Hello everyone, welcome to the Physics 49 Virtual SI session. Today is October 21, and today me and Hassib will be going over vectors and applications of them.
Hello everyone, this is Hassib. So as all of us noticed in class, we've been dealing with a lot of vectors lately, especially with the introduction of problems that involve two-dimensional motion. We start talking about vectors and how can we manipulate vectors um, during a motion that follows a two-dimensional path. And we can ask ourselves, like, why those vectors are important and why should we know how to manipulate them. Well, I'll switch to my iPad and we can start talking about what are these vectors and why they're important, why we're really using it when it comes to two-dimensional motion. All right, let me switch to the iPad. Okay, so what are the 2D vectors? So sometimes motion objects don't move in one dimension. They move in 2 dimensions and 3 dimensions, and we need some notation to keep track of that motion. And this notation is something that we call a vector. For example, let's say we have an object that is right here. That's the starting point. And it's moving to another point, that's the ending point. And we can notice that the motion from here to here is not one-dimensional motion. It moved in 2 dimensions. This is the x and this is the y. And we have a vector that represents it. So the utility of this vector, it would describe the motion from the starting point to the end point. It will tell us the distance from, or the displacement from the starting point to the end point, and it would tell us the components of this motion. And the reason we called it a 2D vector, and let's say we call this vector D1, is it will express the motion in 2 components. And the components we talk about is usually the I component, and we combine it with the J component. And those are also referenced to the J hat could be replaced by Y hat, and the I hat could be replaced by X hat. So for example, the vector D1, it represents a motion in 2 dimensions. That's why it has 2 components, the I and the J. Sometimes vectors don't move, or sometimes motions are not in 2 dimensions, sometimes they are in 3 dimensions. So that means we add another component. And sometimes they're in 1 dimension, and that's what we have been doing earlier in last month in class. And it was only 1 component for the motion. And that's why we did not really focus on putting I or J, because we know it's 1 dimension. But once we start jumping into 2-dimensional motions, we care about the components of the motion. So a 2D vector, it's important that we know that it has an I component and a J component. Those components also have scalar quantities next to them. For example, 3 and 5 right here. And that tells us that in the I or X direction, the object moved 3 units, and in the J direction or Y direction, the object moved 5 units. Also, another utility of vectors is they tell us the direction, positive or negative. So maybe in another case, we could have a negative I hat. And that tells us that the vector is moving in the negative direction on the x-axis. And that's mostly it about the two-dimensional vectors. They are vectors with two components. Those two components are two separate dimensions of the motion. They have scalar values that represent the units in each specific dimension, and we have signs next to the component that tells us is it a positive or negative. So, and that's why they're important. They pack a lot of information. Two-dimensional vectors, they pack the scalar values, the direction, and the component. And that's why they are very important, and we use them a lot in physics. It's almost every time that we have to deal with direction and an amount, like a scalar value, we just use vectors. It makes the work a little bit easy. So that's 2D vectors. Yes, Isaiah.
So for deconstructing vectors in the I and J, you can only do this for vector quantities, correct? Such as velocity?
No, you can decompose.
Yeah, decompose.
You can decompose almost any vector. It doesn't have to be a position vector. It doesn't have to be a velocity or an acceleration vector. In general, vectors can always be decomposed to the components they are made up to, the I and the J. And
okay.
A little bit later on, we will go through what that decomposition could look like.
Gotcha.
But regardless of what the vector represents, we can always decompose them. Okay, now let's jump into some notation. So, how do we write these vectors? So, from the earlier point, we wrote the vector and the components notation, which means that the vector will explicitly say the amount in each component. But there's also a different way of writing vectors. And I will put them here. So I will call the first notation component notation. And an example of that will be, for example, the vector D. That's 3 units in the negative I hat direction with 5 units in the, for example, J hat direction. But the second notation that we can use to identify a vector, it's the magnitude plus angle notation. And how would we do that? So let's apply the magnitude and angle notation on an example vector. So let's say we have this coordinate system. This is my x, this is my y. And let's say we have this vector right here. So what we say in the magnitude and angle notation is that the length of this vector, for example, is 5, and it has an angle of 30 degrees from the horizontal axis, this one. And that's all what we need to identify this vector. So we can say that this is vector D1. It has a magnitude of 5, and it has an angle theta, which is equal to 30 degrees. So those are the two notations that we can see vectors in. We can see vectors in the component notation. We can see vectors in the magnitude and angle notation. And it's important that we also know how to transfer between one notation and another. Because, for example, you can imagine this notation saying that person is walking for 5 meters. For 5 meters. And those 5 meters could be a magnitude of a vector. And we can say that this person was walking 5 meters, 30 degrees away, or like east of south, for example. So this example can show us that, yeah, we can, the utility of the different notations exists in real life. And it's important to be able to know both notations. And that's where we're going to jump into the next point, and where Isaiah is going to walk us through the transformation between those two notations.
Yeah.
Okay, I'll hand you the board, I guess, or I'll hand you the host.
Or you can just stop sharing and then not share.
Okay. All right, go for it.
Okay. Yeah, so when Hassib showed us two ways of making vectors. There's the I and J method where we had like 3i minus 5j. And then there was also the way of when you have the magnitude. Oh. Yeah, the magnitude, and then you had a certain angle here. So the thing is, both of these, the 3i minus 5j and the magnitude and angle, can be essentially related to one another. And the form that we want to go to is this. So when we're writing, in order to transform the angle and magnitude into the I hat and J hat, we need to essentially get the components in the Y and X. So in order to start that, we need to review some trigonometry before we get into decomposing this vector. So if you remember SOHCAHTOA, it's essentially the relationship between a right triangle and then this is a right triangle. And so with a right triangle, SOHCAHTOA can be used to relate the sides of it and the angles besides the 90-degree angle. So let's start off with saying this angle. So if we remember our trig, there's first so, it's sine, opposite, hypotenuse, right? So what that is saying is that the sine, the sine of an angle, we'll say theta, is equal to the opposite side of the angle over or divided by the hypotenuse, as shown here. So what I mean by opposite and adjacent is that the side opposite to the angle, which in this case, this would be the opposite. And then the hypotenuse being the longest side of the triangle. So there's this. And then let's actually color code these. So actually, we'll make this blue. Okay, and now there's ka, and if you were to guess, it'd be the cosine, but there's an a this time. So we have hypotenuse, but this a is adjacent. So what that means is the side that is on the side that's on the same plane as the angle that we're given. So in our case, it'd be right here. We'll make that right. Erase it. So if now for cosine, it'd be that cosine of theta is equal to the adjacent over the hypotenuse. All right, the final relationship that we have in order to decompose the vectors is tangent. And for tangent, it's tan. And we already know what O is, so it'd be opposite. And the final one we know is A, which is adjacent. And then this relationship, you could guess for it to be tan of theta is equal to the opposite over the adjacent side. So if you know all three of these trig relationships, we can move on into deconstructing or decomposing our vector to match the I hat, J hat format. So
Okay.
that's what we're going to do right now.
Isaiah, so we need to know these trig identities to find the components of a vector, right?
Yeah, these are the identities.
So I could have the magnitude and angle, and let's say I want to go back to the component notation, I need to use these identities.
Yes, that's correct.
Okay, but maybe I think I have a specific question about the angle. Like,
yeah,
your angle theta was on the bottom left, and we had adjacent is the bottom side, and the right side was the opposite. But
yes.
would that change if my angle was the one on top?
Yes, it would change actually. So if you were to redraw your triangle, no, let's not use green. If you were to redraw your triangle, right?
Okay.
That's a right triangle. Right?
Mm-hmm.
And let's say we made our theta here. Now, the relationships or the sides that are labeled as opposite, adjacent, and hypotenuse will change because now the right side is no longer the opposite because it's just not the opposite. So the opposite side this time would be, in this case, the bottom.
Oh.
This would be the opposite. And then you could guess which one would be adjacent.
It's the one to the right. Yeah.
To the right. Right here. this would be the adjacent. And then the hypotenuse is, again, always the longest side. So between the three of them, the hypotenuse pretty much never changes.
Okay. So I need to pay attention which angle that I'm using so I can identify the opposite and adjacent, and they might change depending on the angle. Okay,
exactly. I see. So with all this information known, right, let's go back to the example that we have. And just select all this, move it over here. Okay, so let's see, what did we have for our thing? It was negative 3i?
Negative 3i plus 6j.
Plus 6j. Okay, so this is the I hat and j hat form we have. And then we are given here, and then we were given a magnitude of, what magnitude were we given?
Let's do a magnitude of 6.
Okay, so a magnitude of 6, and we'll say at, let's say like 45 degrees.
Okay.
So here, say that this is theta, right?
Mm-hmm.
Let's say that theta is equal to 45 degrees. And it's important that when you do these problems that your calculator is in degrees. Otherwise, all of it gets messed up.
So we're breaking down the vector of magnitude 6 and the angle 45 into the component notation, right?
Correct. That's the whole goal of it.
Okay.
So,
and what is the negative 3i and plus 6j is for?
that's what, this is the desired form we want.
Oh, that's
just in general.
That's the format. Okay, I see.
Yes, in general. So we're gonna turn this, right? We're gonna turn this form right here.
Mm-hmm.
We're gonna turn it into that form.
Okay, and that's exactly what we were just talking about, right? We were using triangles, but there was no coordinate systems. But I think that shouldn't be an issue, right?
Yeah, that shouldn't be an issue.
Okay.
Because you'll see why in a bit. Because the I hat and j hat is gonna make the triangle itself.
Okay.
So we have to make a couple assumptions first that this is a right triangle. And in the rest of our Physics 49, it's gonna be a right triangle. Here. And right. Like this. Okay. So we have 6, right, as the magnitude. What can you say about the 6? Like, what does it holistically represent?
Well, the 6 was the magnitude of the vector, but it's also the length of the vector, right?
Yeah. So,
which makes it the length of the hypotenuse in this triangle.
exactly. That's what the magnitude shows, is the hypotenuse of the triangle itself.
Okay.
So now we're going to break this triangle into its respective components. So we have theta, which is 45. Let me actually write that. 45. And now we're trying to find the missing sides because that's what we want. So if we look at our relationships, let's look at this side first, right? Right here. Let's look at that side. So that side, in accordance to our angle, is the opposite, correct?
Well, the angle was here.
Mm-hmm.
So yeah, if this is the angle and that's the side directly opposite of the angle, so yeah, that would be our opposite. Yeah.
Yeah. So between the three of these relationships, only two have the opposite, the sine and tangent.
Mm-hmm.
The only difference between those two is the denominator, the hypotenuse and adjacent.
Okay.
So with all the information given, we have the angle, theta, and we have 6, which, again, we said is the hypotenuse. So we want the opposite, and we have the angle and hypotenuse. So the only thing that matches that is using sine theta is equal to opposite over hypotenuse.
We know the angle, we don't know the opposite, and we know the hypotenuse. Okay, so we will have like one unknown, and we can solve for it, which is the opposite. Okay.
Exactly. So in this case, we have, and to solve it, we have the opposite is equal to the hypotenuse times sine theta. And then see if you could put that in a calculator.
All right. So the hypotenuse that we have is 6, and we have to multiply it by the sine of 45, and that will give us 4.24.
All right, so let's just do, you said 4.24?
Yeah.
4. Okay. So now that we found that, move this up here, move this up here. Okay. We have the opposite. Now we want to find the adjacent. Now with the adjacent, we have two choices. We could do the tan or the cosine. Let's say, for instance, we didn't know the opposite side.
Okay.
Because we solved for it. But let's say we didn't know it.
If we didn't know the opposite, that means we only know the angle and the hypotenuse again, and we need to find the adjacent. We have to go with the cosine because we know the angle, we don't know adjacent, and we know hypotenuse. So the only unknown will be the adjacent, and yeah, the cosine will work.
Exactly. So we're looking for the adjacent, like you said. And let's say we don't know the opposite, but we know the hypotenuse. The cosine is the only thing we could use. So if we this here, right? And now to solve for the adjacent, we would do adjacent is equal to the hypotenuse times cosine of theta, and that would be what?
For this one, hypotenuse is 6 and its cosine theta is 45. That will give us 4.24 again. And we got the same number as the opposite side. And it makes a little bit of sense because the angle is 45. That means that the other angle on the other side is 45. So the sides should be equal too. Yeah,
Exactly.
4.24 should be a reasonable number.
Yeah, that's the point. If you remember your unit circle, the cosine and sine of a 45-degree angle is going to be the same. So
Yeah, that's right.
we have 4.24 and 4.24. So if you imagine this on a coordinate system, which I would draw in a different color, let's do like blue. Right? Oh, let's do the line. Okay. Right? You can imagine this as a coordinate system.
Oh, now it became like almost exactly like the
Top picture.
Yeah, exactly. Almost looks like exactly like this one.
Yeah. And that's the whole goal of doing this triangle method.
Mm-hmm.
So now we have an x and y. And like Hassib said earlier, the x can be called the I hat and the y can be called the j hat. So now it comes to if this is positive or negative. If we say that right and up is positive, we could see that the magnitude goes both right and up. So therefore, both signs are positive. So then the finished product of this would be 4.24i plus 4.24j. And this is how you deconstruct it or decompose a vector.
So, like, it looks like we can take the vector outside the coordinate system, do the work on it based on a triangle, then return back to the coordinate system with the component values and place it there.
Exactly.
Okay. Damn, those triangles are pretty useful.
It's going to be your life.
And I remember in the class we talked about arc sine and arc cosine, but I didn't really understand it very well. And it was, I think the question was, oh, maybe we know the components, but we want to know the angle. And it's like everybody knew how to do it, and I struggled a little bit with it. Can you
Elaborate.
elaborate on it a little bit?
Yeah. So that's another really common case. So let's say we have, oh, that's a square. Okay. So, oh, where'd my tool thing disappear to? It won't let me. Where are you? Okay, hold on. It's not appearing for me.
What is it?
My thing that lets me do text and all that.
That's weird. It's the board is zooming in and out for some reason.
I'm trying to find my thing.
Okay, you can close the board and open it again if you want.
Yeah, I'm gonna do that. Stop share. And then just gonna do it again. Okay. Okay, there you go. It's back.
Okay.
So, sorry about that. So, that's another common case where we have, let's say we have let's say this is 5. And then let's say that okay, that is a right triangle, trust me.
Okay.
All right, let's say we have, and this is 4, right?
Okay.
And let's say we want to find this angle, right?
Okay.
So in order to do that, well, first off, let's establish what we have. We're looking for an angle. We have the hypotenuse. Do we have the opposite or do we have the adjacent?
Uh, we have the 4. This one is the adjacent.
Yes, that's correct. So which one would we use if we have the hypotenuse and the adjacent?
Hypotenuse, we have hypotenuse and we have adjacent. We should use the cosine identity.
Exactly.
We know those two.
So let's again use the cosine identity. Cosine theta is equal to adjacent over hypotenuse. So now it's the question of how can we isolate for cosine theta, correct? So there's this thing called arc cosine or cosine inverse that we could use to inverse the cosine itself. So if we do cosine 1 of cosine of theta, and then what you do to one side, you have to do to the other.
Yeah.
So once you do that, if you cosine inverse a cosine, they cancel out and all you have left is theta. And then to calculate everything, you put in your calculator the cosine inverse of your adjacent, which in our case is 4 divided by our hypotenuse, 5. And if you put that in a calculator, you will get,
Let me use it. So, oh yeah, that's right. The inverse trig identities are in the calculator too, and we're using cosine inverse 4 divided by 5. 36.9.
36.9 degrees.
And yeah, it looks reasonable for this angle to be 36.9. Okay, I see how it works right now. So yeah, the inverse is the inverse operation of the trig identity. Using that, we can isolate theta on one side of the equation, and we have all knowns on the other side.
Exactly. So this is good. So this process is really good. But now how do we apply it? There's this thing called vector addition, and it can be done both graphically and algebraically. So Hassib will go over onto vector addition graphically.
Okay. I will share. Okay. Right now, we're going to talk about vector addition graphically. So we were just seeing how we can decompose a vector to its components. The I component and the j component. But if we also looked at this case And we noticed the triangles we were drawing. For example, this triangle, we have this vector, let's call it D1. Maybe I should remove this. And when we decomposed it, we found the length of this side, and we found that to be 4. Sorry about that. We found that to be 4.24, and the other side we found it to be 4.24, and this was a 45 degrees angle. And what we also did is we wrote the vector D1 to be 4.24 I hat plus 4.24 j hat. Well, since we decomposed it, when we decompose a vector to its components, we're saying that the vector D1 has two components, this one and this one, and those two components by themselves are separate vectors. So we can look at this one and say this is the vector D1x, and we can look at the other one and say this is the vector D1y because it's in the y direction. And what we're doing in the end of the day is just adding two vectors to get D1. So we're adding the x1 and we're adding the D1y. And we already know how that would look like graphically because we know how we decomposed it. It would also look like a triangle. We know that the vector D1x is this one right here, and it would look something like that. So that's D1x. And we know the vector D1y is a vector that looks like this. And the resultant vector D1 was a vector that spanned from the tail of the first vector to the tip of the last vector, and we got D1. So that should give us an insight into how vector addition work. When we were adding the two vectors, D1x and D1y, we laid out D1x first, which is this one right here. Then we attached the tip, the tail of D1y to the tip of D1x. And that's what happened here. We have D1x and we attached D1y to the tip of D1x. And the resultant vector was D1, the big vector, and that was the result of the addition. So the rule for the addition is the following. We attach the tail of the second vector to the tip of the first vector. In this case, the first vector was D1, and the second vector was D1y. Then the resultant vector is a vector spanning from the tail of the first vector to the tip of the last vector. And in this case, the tail of the first vector was this point right here, and the tip of the last vector was this point right here. And that gave us the resultant vector d1. So that's the addition of vectors graphically. We attach the vectors to each other, tail to tip, and the resultant vector will be from the tail of the first vector to the tip of the last vector. And the addition could also happen algebraically, and this is what Isaiah will go over in a sec.
So confused. So Hassib showed us the graphical way of adding up or vector addition. There's also the algebraic way. So if let's move all this. Okay, so let's say we had Hassib, give me two numbers.
-4 and 3.
3J. So let's say we had this, correct?
Mm-hmm.
And the thing about adding vectors algebraically, you must know the components. So if I was given let's say this, that, and let's say I was given vector 1 and then let's say like vector 2, I would decompose both of these vectors before dealing with how to add them. So let's say we did decompose those vectors. So let's say this is vector 1. And then vector 2, give me two more numbers.
That will be 3 and 3.
3 and 3? Okay, so 3i plus 3j. So adding vectors algebraically, once you do the decomposing, is pretty simple. Everything that's in I, you add together. Everything that's in J, you add together. So in this case, here. So -4 plus 3 is
-1.
-1. And then would it be I or J?
Those are I components, so it should be I.
Yeah. And then 3 plus 3j is
6j.
6j. And that's literally all there is to it for adding vectors algebraically.
Okay. Yeah, that sounds pretty simple. Just add the same components, we add them together.
Mm-hmm.
Then what if one of the vectors did not have one of the components?
Oh, okay. So like, let's say if we go to our graph, let's go. Oops. We go to our graph. You're saying like
what if the 3j did not exist in one of these vectors?
So like this?
Yeah, that's one of them, and another one is
like that.
Yeah.
So we said j's represent the y direction, correct?
Okay.
So that bottom vector right here.
Okay.
Or the one pointing down.
Mm-hmm.
You could say that it has only a j component or y component.
Okay.
And then is it going left or right?
It's not, no.
So there's going to be a 0 I hat or a 0 X component.
Oh, the X component will be 0.
Yeah, that's a good thing to point out.
Okay, and whenever we add the X components, it's just a 0. I can assume it's 0, and the addition will be fine in that case.
So real quick, I could do it really fast. This can be like 5i plus 5j.
Mm-hmm.
And then this bottom one will be 0i minus 6j. And then when you add both, plus sign here, you add both, you'll get 5i minus 1j.
Okay, I see. All right, sounds good.
So finally, we want to go over a practice problem, which Hassib has set up for us. So if we switch to Hassib.
All right.
For the final item on our virtual SI session.
Okay, so the purpose of the practice problem we're gonna go over right now is just to kind of recap almost everything that we went over in this session. So the idea here is that I have this vector, d1, and it's written in the component notation. It's 3 units in the negative I direction and 6 units in the positive j direction. And I have the vector d2, but the catch here is vector d2 is not written in the component notation. I'm only given the magnitude and the theta from the horizontal axis for that vector. And what I'm being asked for is show the components of vector r, which is equal to d1 plus d2. So here we're being asked to add the two vectors to find r, but one of the vectors is not in the component notation. And as Isaiah went over a minute ago, we cannot add two vectors unless we have both of them in the component notation. So what should we do first? The first step will be transforming the vector d2 into component notation. So let's do it right now. So I have, from the information given to us, we have d2. And we know that the length of this vector is 6. And we know that this angle is theta equals to 30 degrees. And I want to break this vector down to its components. So this is the angle. This is going to be my opposite. And this is going to be my adjacent. And I want to know how long is the opposite and how long is the adjacent. So let's start with the opposite first. From our trig identities, we should pick the one where opposite is unknown and hypotenuse and the angle is known. And that trig identity will be sine, because we know that sine of theta is equal to opposite over hypotenuse. And we don't know opposite, so we isolate the opposite, and that's equal to hypotenuse times sine of theta. Our hypotenuse is equal to 6, and we have sine of 30. We know that sine of 30 is 1/2. That gives us 6 multiplied by 1/2, which equals to 3. So the opposite is equal to 3. Now, let's find the adjacent. In this case, what's the identity that we can use to find the adjacent? It's an identity that will use the angle and the knowns that we have, which is the angle and the hypotenuse. And that identity is cosine, because we know that cosine theta is equal to adjacent over hypotenuse. And
So since we solved for the opposite, could we also use the tangent?
in this case, since opposite is known, yeah, we can use the tangent. And I can do that right next to each other. So we can use the cosine, and we can use the tangent, which is opposite over adjacent. And we can point out that in the tangent equation, the only thing we don't know is the adjacent, so we can use it. And the cosine equation, the only thing we don't know is just the adjacent. So both equations would work to find the adjacent. So let's isolate on both equations. So that would give us adjacent equal to hypotenuse multiplied by cosine of theta. And here we will get adjacent equals opposite multiplied by tangent of theta. And let's replace the values with the known values. We know that the hypotenuse here is 6 times cosine of 30 degrees. And here we know that the opposite that we just calculated is 3. And the tangent is tangent of 30. Here, cosine of 30 is, we can just use the calculator to get the accurate numbers. So I'm going to do that right now. We 6 multiplied by cosine 30. And that will give us 5.19. Let's see if we could get the same answer with a tangent one. It's 3 times tangent of 30. And here we got a different answer, which is 1.7. So there is something that is wrong.
So from what I'm looking is that for the tangent, we multiplied the opposite times the tangent, as opposed to the opposite being divided by the tangent.
Yeah, so I did something wrong on this step. My isolation of adjacent was not correct. So to backtrack, this is wrong. And that will be adjacent is equal to opposite over tangent of theta. And that's equal to 3 over tangent of 30. Let's see if that will give us the right answer. So we can notice from here that it's quite easy to make some mistakes while doing some algebra manipulation. So if it was me on the test, I would probably lost a couple points on that. So we need to be very careful. So the result for this one is 5.19. So what we did here is we decomposed D2 to its components, and we'll focus on this section for the solution. So D2 will be equal to 5.19 I hat plus 3 j hat, and we know that D1 is equal
to negative 3i
hat plus 6 j hat. And as Isaiah was doing earlier, we can just add the same components together to get the R, and that's 5.19 plus negative 3. So it's really important to notice that there is a negative right here. So that will give us 2.19 I hat plus 3 plus 6 is 9 j hat. And that would be the end of this practice problem. We were able to find the components of a vector, transform it into the component notation, then that would allow us to do the addition. So it's really important to notice in the end of the session that when we do additions, we can only do additions when all the vectors are in component notation. And that would wrap it up for our session. Everybody, you guys can keep in mind that we have our physical sessions on Monday, Isaiah and me. And any questions on these topics we're open for it. As far as my session, I'll be probably covering a little bit more on vectors. Isaiah, what are you going to be covering for next session?
Pretty much the same thing, just more applications of vectors and pretty much what we did in this practice problem, but various different conditions.
Okay, and our next virtual SI session should be in 2 weeks from now.
So that will be our next virtual SI session, if you could write it down, Hassib.
Yep.
It'll be November 4th.
Sunday, November 4th.
And this time it'll be from 11 to 12.
All right, and that's 11 to 12. Okay, awesome.
All right.
That'll be it for the SI session. Thank you, everyone.